Hello and welcome to Lecture 2 of Dynamics of Circular Motion, and now we're going to get back to looking at forces. So here is the whole point of this lecture. I could have made this lecture 10 seconds long and just say Fnet points to the center in uniform circular motion. Newton's second law tells us A is Fnet over m. And so the net force always points in the same direction as the acceleration, and the magnitude of the acceleration is proportional to the magnitude of the net force. Well, in uniform circular motion, we know that the acceleration always points to the center of the circle, and so Fnet must as well. And we now have a way in uniform circular motion that we can determine the magnitude of A, or put the magnitude of A in terms of V and R, and so that's often useful when solving Newton's second law. Here's a piece of terminology I'm just not going to use, but I should introduce it to you so that you recognize it when you see it elsewhere. Lots of textbooks will use the term centripetal, and it just means center seeking. So when we say a centripetal force, we just mean a force pointing to the center of the circle. Centripetal acceleration, well, acceleration pointing to the center, just as it always does in uniform circular motion. But I really find this is unnecessary. Why don't we just say the net force and the acceleration point to the center? So I'm not going to bother with these terms. I find they just confuse students. And so as a general principle, we should perpetually eschew obfuscation. Right? That's clear. Perpetually means always. Eschew means avoid. Obfuscation is making a meaning unclear or hiding the meaning. So in other words, we should always avoid using words that are more complicated than we need. Let's start off by thinking about me swinging this water bottle around. So you can see the water bottle going around in a circle over my head. And if we just pause it right there, I want us to think about it at this moment when it is over here. And notice that the only thing touching it is this string right here. So we might be able to find the tension in the string here. That actually turns out to be a bit of a difficult problem, and we won't be ready to do it until next lecture. But for now, we can at least draw the free body diagram. And the first thing to think about is the perspective to take. It might be tempting to think about a top view like this. But if you think about it, now there's a weight acting on this bottle, and in this picture the weight would be into the page. The tension is actually up at an angle out of the page, and you just can't convey that information in a free body diagram if you think of a top view like this. Instead, it's better to take a perspective like this, where you ensure that all of the forces end up in the plane of the page. So here, the velocity vector is out of the page. Now, we're not putting the velocity vector on the free body diagram. We never do that. The only vectors that go on free body diagrams are forces. And then the other thing is that the center of the circle is to the right in this picture. Now there's nothing special about V out and center to the right. I could choose to look at the bottle over here, in which case V would be in and the center would be to the left. And a few things to notice before we start drawing the free body diagram. The only thing touching the bottle is the string, and we know what that does. It exerts a tension. The other thing to notice, if you look at the video, is that the string is not horizontal, and we'll eventually see why it can't be. So we're now ready to draw the free body diagram. As always, we'll have the weight down, and the tension, as always, acts along the direction that the string points. And now the net force, we know that in uniform circular motion, the net force acts into the center, and in our picture that's to the right. So that's as far as we're going to go with this. I will stick the axes on, but we're not ready to work this yet because there are several difficulties that come out. In particular, the first thing you have to think about is the radius of this circle. Let's watch me swinging this bottle around again, but this time I'm swinging it around on the floor. And one thing about this time is that the bottle is rolling on the floor. So the main friction on it should be rolling friction. That's generally quite small, and so we're going to ignore it. So let's now find the tension in the string. I've made some measurements. I've got the radius of the circle by measuring the string. I slapped the bottle onto a kitchen scale, and I looked at the video to determine the period, very much like I did in the last lecture. And so let us go straight ahead and draw our free body diagram. And I'll use the same perspective with the velocity out of the page and the center of the circle to the right. So as always, there will be a weight, and the bottle is in contact with the floor, so there will be a normal force up. There should be a friction, but it's a rolling friction. We're going to neglect it. If we put it on, it would actually be into the page, so that's kind of hard to draw anyway. And then the tension points along the length of the string, and that is horizontal this time, which is why this one comes out simpler than the other one. So there is our free body diagram. And again, we know the direction of the net force. This is uniform circular motion, so the net force is into the center like so. And now all of our forces are either up or right, and so it makes sense to set our axes like so, nothing fancy. And so our next task is to translate that free body diagram into a statement of Newton's second law. So our sum of x components of forces and our sum of y components of forces, and this is going to be nice and simple, because in the y direction all we've got is the normal and the weight, and we know Fnet has no y component, it's horizontal, and so there we go. And in the x direction all we have is the tension, and so that'll equal max. And I'll just take a moment to point out something. Oh look, this is period, this is tension. We can't have that. We shouldn't use the same symbol for two things. So I'm going to use F sub t for my tension this time, so that there's no confusion between the tension and the period. And if you count unknowns, you notice, first of all, this is what we're looking for. And we don't know the acceleration. And down here we don't know the normal. We know the weight, that's just mg, and we know m. However, this equation isn't going to be useful to us. Look, the normal doesn't come in here at all, so we can just ignore that. But that still means we have one equation in two unknowns. However, here's where our knowledge of the motion comes in again. So this is uniform circular motion, so we know the acceleration is v squared over r. But that may seem like it doesn't help us so much because we don't know v. Except that we have enough information to get v, because as we saw in the last lecture, if you know any two of v, r, and t, then you can get the third. And so we can use that v is the circumference over the period. So I'm just going to start back substituting now. The acceleration then is 2 pi r over the period squared all over r, and so that is 4 pi squared. R squared over r leaves r over the period squared, and I can now plug this up into here, and I've solved for the tension. M times 4 pi squared r over t squared, and it's time to plug in numbers. So before plugging in, note that we always want to work in MKS units. So this radius is 0.56 meters. If we don't work in MKS units, our units do very funny things to us. Our mass is 0.04 kilograms. This is already in seconds, so we're good. And if you don't do that, then you're going to get an answer that's off, and we'll see why. So do a quick unit check. I've got kilogram meters per second squared. and that is indeed newtons. Now, if you didn't remember to do your conversions, and if you just plugged in numbers without carrying your units and didn't look at your units, you would have gram centimeters per second squared. And a gram centimeter per second squared is not a newton, so you would be off by a rather large factor, actually. Anyway, doing that, we get newtons, and so we're good. And plugging it into the calculator, we find it's 0.52 newtons. Let's work one more that illustrates another few points. Here's a car, and let's say it's coasting in neutral, and it came along the road and dipped over this edge of the hill down into this valley. And this doesn't look like circular motion, but if the bottom of this valley has a curvature that is part of a circle, then at least this little piece of the motion is circular motion. So I'm going to say this radius is 150 meters. Now, there's something else subtle going on here, because the car would have been speeding up as it came down the hill. But then it should be slowing down. Remember, it's coasting in neutral, slowing down as it goes up the other side of the hill. And so, although this isn't uniform circular motion, down here at the bottom, it is neither speeding up nor slowing down. And so right there, the acceleration would point straight up, straight into the center of the circle. And so this moment is what we would call instantaneously uniform circular motion. As a whole, this isn't uniform circular motion, but this one instant can be treated as uniform circular motion because the acceleration is straight into the center. In other words, it's not speeding up or slowing down here. And so we can go ahead and draw our free body diagram, and it's particularly simple. There's going to be the weight, as always, and the road is going to exert a normal force on it, and there could be friction, but like I said, it should just be rolling friction, so let's ignore it. And that's everything. We have our normal, we have our weight, and we know which way the net force is. It acts into the center of the circle, which in this case is straight up. And every vector we have is either up or down, so we don't even need full axes, though I'll put them on anyway. We might as well put our y-axis straight up. And now we go ahead and convert this into a statement of Newton's second law. And what we're going to find here is the normal force acting on the car. So there are no x forces, so we don't even care about the x components. So all we have are the y components of the forces, and so that is just a normal minus a weight, and that will equal ma(y). And counting unknowns again, we don't know the normal, that's what I said we're looking for. We don't know the acceleration, but we do know the mass, and so therefore the weight is just mg, and I'll call that a known then. And we have two unknowns in one equation. But again, this is uniform circular motion, so our acceleration is just v squared over r, and in fact this time we just know v. And so we're practically done. N minus the weight, which I might as well write as mg, is m v squared over r. And so n is just m v squared over r plus mg, which you could write this way. It's a little simpler. And we'll talk more about this next lecture. If you want, you can plug that into your calculator and get a number, but I'm going to call myself done.